thank you so much for having this delightful workshop that fortunately is in the middle of my spring break. Next week, I'll be teaching 1,000 intro bio students, so that'll be quite a different audience. I wish I could be there with everyone. I'd love to be at the Institute and seeing everything live, but unfortunately that was not to be this time. So the question that I'm going to look at is an old question. It's trying to understand the distribution and abundance of plants and animals. For instance, trying to understand the distributions of these two species of thrushes in the Smoky Mountains in North America. And one approach to understanding how species might be distributed is understanding their habitat selection. And one of the first studies about habitat selection was done by a person who had the following quote. He had stated, "I was studying earthworm brains for my doctoral dissertation. I was irritated by David Lack's dogmatic position that territorial behavior did not affect habitat selection. In desperation, I put it all into mathematical models and made several wondrous discoveries. I soon dropped the earthworm research. Both the worms and I were having nervous breakdowns and getting nowhere." So this is a quote from Stephen Fretwell, reflecting upon his citation classic with Lucas, in which they introduced what's known as the ideal free distribution. So we heard a little bit about the ideal free distribution earlier today in Fritjof's talk. And in this context, we're envisioning a patchy landscape, so there are different habitat patches in which the species can live. And we'd say they're exhibiting an ideal free distribution if their per capita growth rate in all of the occupied patches are equal, but would be lower if they went to other patches. So this would suggest this is an evolutionary stable strategy, but it took several decades before it was shown mathematically to be an evolutionary stable strategy. In other words, a strategy that if adopted by most of the population would resist an invasion attempts by mutant subpopulations. Now, these evolutionary stable strategies were mostly formulated in the context of equilibrium conditions, and they have several implications. For single species, it implies in particular that there are no sink populations, populations where the per capita birth rate is less than the per capita death rate. They also give insights about how species might be distributed across space if the main source of spatial heterogeneity is resource availability. So for instance, in these experiments with stickleback by Malinsky, you might have one patch is the left-hand side of the tank, the other patch is the right-hand side of the tank, and there's greater food availability, 5 times as much on the left-hand side of the tank than on the right-hand side of the tank. And the ideal free distribution would say that if this is the only source of heterogeneity, this fish should distribute in such a way that they have equal amount of resource per individual, and therefore you'd have 5 times as many fish on the left-hand side than on the right-hand side. And indeed, that's what was observed in the experiments done by Malinsky in the 1970s. The ideal free distribution not only has implications for single species, but also for species interactions. One of the most classic ideas relates to mutualistically antagonistic interaction of competition. So perhaps we have these two competing bird species, these two warbler species, along an altitudinal gradient. And maybe historically their distributions were overlapping. This is hypothetical distributions right now. But the ideal free distribution says there will be selection for them to fully spatially segregate, as is observed in nature, so that the species that's competitively superior at the higher altitudes just stays in the higher altitudes, and the species that's competitively superior at the lower altitudes just stays at the lower altitudes. And this leads to what's known as the ghost of competition past, because even though by being spatially segregated, the species are not competing, it's their past competition that led to their spatial segregation. However, even though these things I just described related to the ideal free distribution exist in nature, we often find that there are sink populations. For instance, in this meta-analysis done by Fur and Passanelli, they found many, many taxa where the number of sink populations was similar or even more than the number of source populations. Moreover, as I showed in my initial slide, co-occurring competitors are often common. So we can start asking, well, what might explain through evolution for these sort of patterns? And some theory for single species looked at the factor of temporally varying environments. and found that that can select for single populations and input mismatch, but it really didn't consider what happens if you have interacting species included in this mix. So the question that I'm talking about today is, what effect does spatial and temporal variation have on the coevolution of patch selection in meta-communities? And the way I'm going to approach this question is, first I'm going to describe some stochastic differential equation models of species competing or interacting in space, talk about what coexistence even means in those models so that we can say how do the coexisting species co-evolve. And then I'll get into the main results for this talk, which are about what is coevolutionary stability for these stochastic models and how can we characterize it for patch selection. And then I'll look at some applications to antagonistic interactions, competing species, and predator-prey interactions. And finally conclude by talking a little bit about the relationship of this work to the Nobel Prize-winning work of modern portfolio theory, and then make a few concluding comments. So let me begin with the models and what coexistence means in those models. So these models are going to be adhering to the KISS principle, which is not named after this 1970s band, but rather is an acronym for keep it simple, stupid. Because when it comes to the complexities of nature, I, for one, am inherently stupid. So how am I going to keep it simple? I'm going to do several horrifying things to, I'm sure, many of you. First, I'm not going to treat space explicitly, but rather implicitly. So those lovers of reaction diffusion equations, my apologies. Perhaps maybe even more horrifying, I'm going to assume that we just have mass action dynamics. So those who love type 2 functional responses, the Lee effects, my apologies. And then perhaps the most horrifying thing of all, I'm going to assume that the environmental fluctuations can be represented by multivariate Brownian motions. And for those much more interested in other forms of environmental variations, my humble apologies. But nonetheless, with these simplifying assumptions, I move forward. So what is the model? The model is going to consider k discrete habitat patches and n species, where n can be any natural number. In this case, I'm showing it as if there were 2 species. And then what I'm going to keep track of. So first, I'm going to look at the dynamics within a single patch. Let's call that patch L. Okay. And in that patch L, it's going to be Lotka-Volterra style dynamics. So I'll have the intrinsic rate of growth for each species in that patch. I'll have the interaction coefficients of all the species in that patch. And notice I'll be using a certain nomenclature throughout this talk, which is the subscripts will correspond to species and superscripts will correspond to patches. Okay. So, and what I'm going to keep track of in this patch, in these patches, are the density of each species. So if we just consider the deterministic component, we have a Lotka-Volterra equation and written in sort of an infinitesimal form so that I can write down the next component. Sorry, I should indicate here that I'm going to be denoting this per capita growth rate, which is a linear function of the densities, using the F, and I'll be using that notation throughout the talk. But now to account for environmental stochasticity, I'm going to imagine a Brownian motion for species I in patch L, and so then I'll be adding the infinitesimal of that Brownian motion to create this stochastic differential equation. And now we have a system of k stochastic differential equations, n stochastic differential equations for all the species in this one patch L. But of course, I want to couple the species across the patches. So the way I'm going to do that is in 2 ways. One is implicit space. So I'm going to just keep track of the total density across space and assume there's a fixed proportion of each species in each patch. And these PILs, where the subscript is the species, the L is the patch in which they're in, is going to correspond to what I call patch selection strategy. And then the local densities is just given by multiplying these proportions against the regional densities. So for the deterministic component, that gives me this system of n differential equations, where all I've done is take the spatial average across the different patches. But then I also have coupling through the environmental stochasticity. So for each species, there's k-dimensional multivariate Brownian motion that has a covariance matrix that describes the spatial correlations in the temporal fluctuations between the patches. So that when I put that all together, I get these n Lotka-Volterra stochastic differential equations that implicitly account for space. And just as I said, they are just overdressed Lotka-Volterra stochastic differential equations, just renaming the parameters, including using the patch selection strategies. You just end up getting a standard stochastic Lotka-Volterra differential equation. And the good thing about that is there's a very nice method for determining are all the species coexisting in some sense that I'll describe in a moment. And the conditions involve what we call the Hofbauer criterion. This is named after Joseph Hofbauer, sketched in the lower left. And these conditions for the stochastic differential equations was first derived by me and then done much more completely by Alex Hening and Dan Nguyen, the collaborators on this work. And the important thing about these conditions is that they reduce, at least for the Lotka-Volterra equations, to solving systems of linear equations and solving a linear programming problem. So what that means is it's very easy to do either by hand or numerically. Okay, so what do I mean by coexistence here? So I'm going to mean coexistence means that you have a Borel probability measure on the state space that puts none of its weight on extinction. So all of its weight is on the strictly positive orthant. And moreover, that you have convergence of the empirical measures whenever you start with all species initially present with probability 1. So what that means is for any L1 test function with probability 1, the temporal averages of that test function as time goes to infinity converges to the average with respect to that coexistence measure. And the coexistence criteria in particular imply the function phi of x equals xi, so the projection onto the ith density is an L1 function with respect to this measure. And therefore, in particular, the mean density is well defined. And conveniently, one can show that that mean density, those mean densities are a solution of a system of n linear equations. So once again, they can be solved for quite straightforwardly. Okay, so that's the model, this implicit space stochastic differential equation. That's the notion of coexistence, sort of a unique positive stationary distribution that things converge to. And for those things, everything can be computed by looking at linear equations or solving linear programming problems. So now let's get into the real heart of this talk, which is talking about coevolutionary stable strategies for patch selection. So what I want to make precise over the next few slides is what do I mean by a coevolutionary stable strategy? In other words, what do I mean? Your invasions will fail, mutants. So let's envision we have a community of these n species that are playing some resident strategies. So that would be a matrix P, where each row of the matrix, which is of length K, would be the patch selection strategy for a given species. And let's assume that that resident community playing that strategy is able to coexist in the sense that I described before. So that means they have well-defined mean densities that are all strictly positive. So this is the resident populate community. What happens if you have a subpopulation of some species, I tilde in this case, playing a different patch selection strategy, Q in this case, where again, this is a row vector that's telling you what fraction of this mutant population is in patch 1, patch 2, up to patch L, a K, and we'll assume that that mutant has a density Y, which is a scalar. Then what we can do is write down the expanded version of the equations where you take the resident dynamics, augment them with a mutant, write down the mutants dynamics, and then ask the question if the mutants are truly introduced at very low infinitesimal densities, are they able to invade or not? And one can do that by defining the Lyapunov exponent associated with that coexistence measure in the direction of the mutant, which we'll call the invasion rate of a mutant of species I tilde against the residents playing strategy P, where the mutants are playing strategy Q. And this invasion rate you can write down explicitly, and the main thing I want to mention here is it consists of two pieces. The first piece is the weighted average of the local mean per capita growth rates, where the weights are given by the mutants' allocations to the patches. And the second term, this negative term, is minus a half of the environmental variance being experienced by the mutant. And what we can show then is if this invasion rate, the Lyapunov exponent, is negative, then if mutants are introduced at very low densities, there's a very high probability that they go asymptotically extinct. And in many cases, you can show that they always go extinct, even if they're introduced not under low densities. So since these invasion rates characterize when mutants can invade or not, it's natural to define a coESS in terms of them. And so we'll say this collection of patch selection strategies for all the species in the resident community is a coevolutionary stable strategy, coESS for short, if for every species I tilde with a mutant subpopulation playing a different strategy Q that's different from the resident strategy, that the invasion rate for those mutants is negative. So that gives us a definition of a coevolutionary stable strategy. Moreover, it's a definition that can be checked by looking at systems of linear equations. So it's very easy to compute numerically and in some cases analytically. Okay, but what can we do with that? Is there some way to simplify the problem further? So we can use the method of Lagrange multipliers to get a characterization of the coevolutionary stable strategy. And this characterization will involve four types of quantities. The first quantity is the mean regional growth rate. In other words, on average, across a species I in this case, what is its mean growth rate over time when you're averaging across space and time? The second set of quantities is given by these, the second set of quantities is given by these mean local per capita growth rates, which you're averaging across space to get the regional mean per capita growth rate. This next set of quantities is determined by the environmental fluctuations. So in white here, what I'm plotting is the spatially averaged environmental fluctuations experienced by species I. And then in yellow, I'm plotting the fluctuations experienced by species I in patch L. Now, associated with that pair is a covariance. So the covariants are the next set of quantities I'm interested in, which are the covariation between the fluctuations in patch L and the average fluctuations experienced by the species. Now, these covariances, if you add them up in a weighted way, actually give you the regional variance experienced by the population. And that's the final quantity that's needed for the characterization. So to summarize, we have mean quantities at a regional scale and at a local scale, and then we have a variance at a regional scale, and then the contributors at the local scale. And the necessary condition for being at a coevolutionary stable strategy is the following. There are quantities that are equal across all the occupied patches, and that quantity is the difference between the contribution of a patch to the mean rate of growth and the contribution of that patch to the environmental fluctuations experienced at the regional scale. So this difference is equal in all the occupied patches. What is it equal to? It's equal to the difference in the mean regional growth and the regional environmental variance. And that difference is always strictly negative because the regional growth rate, which has to be zero because we're at stationarity, is the mean minus half the variance. So that's in the occupied patches. And then that equality becomes a strict inequality in the unoccupied patches. So the difference at the local scale is strictly less than the difference at the regional scale in all the unoccupied patches. So there are several implications that come from this sort of necessary condition for the coevolutionary stable strategy. One of them is that if we look at what's equalized across the occupied patches, it's quite different from what you would find in an ideal free distribution, or you could view it as a generalization if you want, but different in the sense that in ideal free distribution, a purely local quantity, the per capita growth rate, is equal across all the patches. So local information determines whether or not things are an ideal free distribution. On the other hand, here, when you have environmental stochasticity, it's actually this local mean per capita growth rate, but also this covariance of the local fluctuations with the regional fluctuations experienced by the population that has to be accounted for. So in particular, local stochastic growth rates, which are the local mean growth rate minus 1/2 the local variance, are not usually equalized across the landscape, which some people have conjectured earlier incorrectly. There's another important consequence of this characterization of the coevolutionary stable strategy, which is that you get a basic dichotomy. Either for a given species in this community, it only occupies one patch at the coESS, or it occupies multiple patches. That's a boring dichotomy. But if it occupies multiple patches, then in all those occupied patches, the local stochastic growth rate is strictly negative. What that means is if you forced a subpopulation of that species to remain only in one of those patches for all time, that subpopulation would be going exponentially fast to extinction. So that means all these subpopulations are stochastic sinks. Okay, so that is a characterization of the coESS with some implications. Let's look at how we can use that characterization for the case of antagonistic interactions. So I'm going to first look at mutually antagonistic interactions of competing species. So let's envision we have two competing species, like these two warbler species drawn here. And let's assume it's a very symmetric scenario at first, because that's where the analytic work is much simpler. So you have an equal number of patches for the orange species and the yellow species, in which they're competitively superior. So in the yellow patches, the yellow species is competitively superior. Its intrinsic rate of growth, R1, is greater than the other species' intrinsic rate of growth, R2. And I'm going to assume that difference in intrinsic rates of growth is this delta R, which is strictly positive. And the other patches, the orange patches in this case, we have species 2 intrinsic rate of growth is delta R greater than species 1 intrinsic rate of growth. And for simplicity, I'll just assume there's the same amount of environmental fluctuations in each patch and that they're spatially uncorrelated. What we can show then is an analytic characterization of coESS using what I talked about earlier. And the first thing that characterization says is that the environmental fluctuations in the patches, the V term, is sufficiently small relative to this delta R, the difference in the intrinsic fitnesses, then you get complete spatial segregation of the two species and the ghost of competition past emerges. Each species only resides in the patch in which they're competitively superior, i.e. have the larger intrinsic rate of growth. However, as soon as you exceed that level of environmental variation, there's selection for at least a partial exorcism of the ghost of competition past, so that each species will occupy all patches, even the patches in which they're competitively inferior, which I'm going to call sink patches because they're conditionally a sink patch for each species. So here I'm plotting just as an illustration numerically how the fraction of each species, what fraction of each species is in the patches in which they're competitively inferior. That's what I mean by sink here. So when the environmental variation is low enough, so you're below this threshold here, then there's complete spatial segregation. They're not occupying the patches occupied by the other species. But as soon as the environmental variation gets high enough, you see a selection for higher and higher fraction of each species to occupy the patch which they're competitively inferior. Further and further sort of exercising the ghost of competition past. Okay, so that's an example where I can do the analysis. How about let's do an example where doing things by hand would be extremely challenging, certainly probably impossible for myself. So for that we'd need some sort of numerical approach. So I'm going to just briefly describe a numerical approach where you use these invasion rate expressions, which I'll remind you are just to term by solving linear equations. And you write down a replicator type dynamic. I won't get into sort of an evolutionary argument that might give you these types of equations, but you get a replicator type equation where the things that are, quote, replicating are the patch selection strategies. And what is in the sort of replicator part of the equation is the gradient of these invasion rates with respect to the mutant allocation strategies across the patches. And it's easy to show that the equilibria of these differential equations, so this is deterministic, this equations, satisfy the necessary conditions for the coESS. And all the numerical simulations I've done thus far show that these equations are converging to equilibria. Moreover, they're converging, appears to be a unique stable equilibrium, which seems to be the coESS. So just to illustrate the use of this numerical algorithm, let's imagine we have three species, the blue, the green, and the yellow, along an altitudinal gradient that's been tilted horizontally. And I'm plotting here the intrinsic rate of growth for each of these species. That's the only way they differ across the patches. And we can see that the blue species has is adapted for the low elevational gradient, lower elevations. The yellow species is adapted for the higher elevations, and the green species in between. And then I can apply that algorithm to say, well, what happens if there's no environmental stochasticity? What do we see? And the algorithm correctly finds that you have an ideal free distribution. So if the species do not occupy the patches where there's a negative intrinsic rate of growth, and they're perfectly spatially segregated. The crossing of lines here is just because this is discrete space, and I was drawing the connecting lines. So the species are just segregating into the patches where they're competitively superior. Now, if I add environmental fluctuations to make it a stochastic model and use this algorithm to solve for the coESS, what I see is there's partial exorcism of the ghost of competition past. So in the middle of this gradient, altitudinal gradient, we see that all three species are coexisting or co-occurring rather. And then at the edges of this gradient, we also see the three species are co-occurring despite the fact that their intrinsic rates of growth are negative there. So these are very hard sink populations that are almost co-occurring at equal frequency in those locations. Okay, so that's an illustration of how you can get this ghost of competition past being partially exorcised and perhaps a slightly more realistic landscape. What about the other form of antagonistic interaction where it's a predator and a prey interaction? So I'm going to talk about an example where it's just some analytic work where we have two patches, a source patch and a sink patch. In the source patch, the prey have a positive intrinsic rate of growth, and in the sink patch, they have a negative intrinsic rate of growth. I'm going to assume that there's environmental fluctuations only in the source patch, and they're only directly affecting or primarily affecting the prey species. In this case, again, you can use that characterization of the coESS from the previous section of my talk to find analytic solutions for the coESS for both the prey and the predator. And it turns out there's three critical values of environmental fluctuations in the source patch for the coESS. So if the environmental variation is below this first dashed vertical line, below V star, you get both species only make use of what I'm calling the source patch, the patch where the prey has a positive intrinsic rate of growth. If now we're between that first threshold and the second threshold, the prey start making use of that sink habitat, but the predator remains in the source habitat. So you have sort of an enemy-free sink. Then if you get to the next level of environmental variation, so this between V double star and V triple star, you get both species make use of both habitats. And then finally, when you get even to a higher level of environmental variation, the predator stops using what was called the source habitat, although at this point, environmental fluctuations are very high there, and only makes use of what I was calling the sink habitat. So we get this very dramatic shift on the habitat selection based on the amount of environmental variation. The other thing that you can solve for here too is the mean densities, these are the mean regional densities of both species, how they vary at equilibrium at the coESS as you vary the amount of environmental variation. So for the predator, the regional density just goes down as you have more and more environmental fluctuations. That's not very surprising. But what's more interesting is even though the prey is experiencing more and more environmental variation as I go from left to right here, you can see that the mean prey density can go up. So even though you're adding something that is first sight harmful to the prey. More environmental fluctuations usually have a negative impact on population abundances on average. The prey density goes up. And that's because of the evolution of selection to make use of the sink habitat. So you sort of have this evolutionary hydra effect. You do something that harms the prey, the variance increases, and over evolutionary time, the prey actually get more abundant. So like the mythical creature knocking off one of its heads to come in its place. So now I'm going to start wrapping up. So I'll briefly talk about how this work relates to the economic theory of modern portfolios, and then give a finale. So the modern portfolio theory is certainly not modern. This is probably why you shouldn't call any theory of yours modern. This was developed in the 1950s by Harry Markowitz. It won a Nobel Prize in economics. And despite being an old theory, according to Investopia, it's still a hip theory, meaning that actually it's used a lot by investors. And what is the idea for the modern portfolio theory? You have different stocks and bonds that you can invest your wealth into, and you make a portfolio of those things, so investing different amounts into the stocks and bonds. Why is that relevant for our for the models that I'm looking at? It's because you can view the different stocks and bonds as different patches that species can allocate individuals into. And associated with those stocks and bonds are mean returns and the risk associated with those returns, the variance, just like the species are having mean growth rates and the environmental variance, the fluctuations in the growth rates that they're experiencing. So what is a good portfolio? According to Harry Markowitz, it's more than a long list of good stocks and bonds. It's a balanced whole, providing the investor with protections and opportunities with respect to a wide range of contingencies. In other words, you have to consider the risks, not just the mean returns. So what Markowitz did in the modern portfolio theory is introduced a very simple plot and way of thinking about portfolios of stocks and bonds. So in this plot, you have the mean in the vertical direction, the mean return, or in our case, the mean growth rate. And on the horizontal direction, you have the risk, which in this case, I'm scaling to be 1/2 the variance. And then you can, for each patch or stock and bond, you can say, what's the mean growth rate? What's the half variance there? And that's the x's. And then you can make portfolios of those. In other words, look at allocating individuals across different patches or investing into different stocks and bonds. And what Markowitz discovered is something called the efficient frontier, which says if you are willing to take on a certain amount of risk, there's going to be a portfolio that will maximize the mean return given that level of risk. And that will lie on this efficient frontier. That point, interestingly, will also correspond if you have a certain mean return that you want, there's a portfolio that minimizes the amount of risk. So all those points define the efficient frontier. Now, the coevolutionary stable strategy has to lie on that efficient frontier. If it did not, then you could get a different patch selection strategy, which would either increase your mean without changing your variance, or decrease your variance without decreasing your mean. Either case, that strategy would be able to invade. But where along this efficient frontier could the strategy lie? So it turns out it has to lie where the mean is equal to 1/2 the variance. That's the 1-to-1 line, because at stationarity, the regional population growth rate has to equal 0. So that point of tangency is the coESS in this modern portfolio theory, and it has a name in the portfolio theory. It's called a tangency portfolio. Now, I won't get into why it's called that and how it relates to having a risk-free investment. Okay, so that means there's already a sort of interesting relation between these coESS work and the modern portfolio theory. And interestingly, you can see that if you're below the white line, it means you have a negative stochastic growth rate because the mean is less than 1/2 the variance. And coESS is on the white line, and all the individual patches, which are the x's, are below that white line, meaning that you have negative stochastic growth rates in all the occupied patches. So to finish up, I used a keep it simple because I'm stupid framework to extend prior work on evolution of patch selection to meta-communities experiencing spatial and temporal variation. I've shown that there's sort of some generalization of the ideal free distribution here, where some difference between the contributions to the mean and the regional variance is what is equalized across space, but that's not purely determined by local quantities. Furthermore, that one can see that temporal variation and species interactions in a spatial context can select for sinc populations, and those might be unconditional sinc populations or sinc populations that are dependent on interactions with other species. You can exercise the ghost of competition past, at least partially, and then you can find these hydra effects over evolutionary timescales. Now, obviously, this is just the tip of the iceberg as far as possibilities to explore, because there are many other types of species interactions one could consider, many other types of landscapes one could consider. And hopefully some other people will find enough of this work interesting and useful enough that they'll explore those other possibilities. So with that, I'd like to thank you very much for, especially for those of you in Paris, being here so late and listening. National Science Foundation from the United States for funding this work, and happily answer any questions that you might have. So thanks. Oops.
Thank you very much. Are there any questions? Maybe I can start. Is there a notion? Maybe I missed some point. Is there a notion of viability in your model? Maybe the simplest one, the one without the prey and predator interactions. Because I suspect, and I think you raised this point, that if you increase the variance too much, that it might happen that all populations just go to extinction. So
that's right. So yes, I didn't show that in these plots, but yes, I was never going past the amount of environmental variation where you'd be losing one or more species. But certainly that's part of what one can look at in terms of, like, when you're looking for the coESS, does it even support all species or not? For the examples I did, it does support all the species over the range that I showed. But that's part of the process that is more on this earlier work where we have conditions for stochastic coexistence as well as for extinction for these stochastic, these Lotka-Volterra stochastic differential equations.
Thank you. And another curiosity question for me is, if I understand right, there is no like physical migration in your model. It's more allocation of frequencies and habitats. Would it be possible to get the same or similar conclusions with a model with physical migration, and individual will allocate or with the migration rates with the strategies? And
yeah, right. So that's a great question. I mean, it's obviously a much harder question, as we've heard from some talks where, I mean, people are certainly in reaction diffusion equations, as well as, I guess they're doing really in all sorts of models, looking at, well, do you have, when is an ideal free distribution stable in those contexts? And some work also now with Adrian on what happens if there's spatial and temporal variation, where in that case, they're allowing the migration patterns to, be active, not, in my case, it's a fixed pattern, not only fixed in multitude of ways. In other words, the distribution is staying constant, but it's also, even if I relax that, I would be assuming that the fraction leaving is constant. But the cases where people look at the ideal free distribution, temporal spatially variable environments, and it more recently has been where, you're tracking the environment changes. So that there is work in that direction. It's hard. And I think some of that, my guess would be things that are at least close to this end of like this idealization that I've set up might reflect similar things, but until it's been done, it's hard to know. But at least based on some of the single species stuff I've seen, it seems to be some of the predictions we're getting by doing implicit space still seem to hold to a certain extent when you have the explicit space with no limit to the amount of dispersal that you can do, meaning that it can be fast dispersal, but whether you disperse or not is maybe is the decision that's being made or the thing that's being selected on. Yeah, so that's sort of maybe not a very clear, rambly response to your question.
Thank you. Are there any other questions?
Is there time for a question?
Sure, please, Adrian, please.
Oh, hi, Sebastian. Nice talk.
Thank you.
I think your model is very it's amazing in that you can calculate many coevolution ESS, so I just want to make sure. So both the prey and predator are at ESS, right? So
yes,
both of their patch selection. Okay. So I'm a little bit curious about the example where you have one sync patch without noise, and then there's a larger patch that is subject to fluctuation. And as the fluctuation goes big, then the predator is 100% in the sync.
Yep.
And is there some intuition? I cannot figure it out. So
yeah.
Is there some intuition why the prey didn't avoid the predator or something?
Oh, okay. So I also thought you were going to ask, is there some intuition why the predator is not using what I was calling, quote, the source patch? Well, I mean, in some ways, like that scenario is like the flip of the first threshold, where there's also selection for the prey to make use of what we call the sync habitat. And you could view it as like sort of a symmetric version of that in some sense, in that when you add enough environmental stochasticity, the source habitat effectively is not really a source habitat anymore, meaning that the stochastic growth rate of the prey is negative there. But because of the bed hedging aspect, actually I have to be able to, let me just be careful here. Right. So maybe, okay, sorry. Let me take myself back a step. Sorry, I spilled a little water and I was trying to avoid destroying some electronics. So there's two things. One, in that case where there's high enough environmental variation where the source habitat effectively is now sync habitat, the prey is still using both habitats, because if it didn't, the prey would go extinct, because both habitats are effectively syncs. So that's why the prey are in both habitats. Now the predator has now shifted just to what I was calling the source habitat, because effectively what was the source habitat has really become, in a stochastic sense, a worse sync habitat. In other words, the prey numbers that can be sustained there are in general lower than in the other patch. So that's why you're sort of getting an inversion of the source and the sync by increasing the environmental variation in the quote source habitat. And that leads to sort of the symmetric result of when the predator is only making use of the better habitat of those two. I don't know if that helps answer the question.
Yeah,
but that's
it's very helpful. Yeah, I can see the significance of your fitness is now habitat quality minus the corrected by the fluctuation.
Yeah, and that's why maybe I should rethink calling it a source and a sync, because maybe it's the stable habitat and the unstable habitat, or something. So when I make the unstable habitat much more unstable, it becomes the lower quality habitat.
Thank you, Sebastian.
Sure. Thank you for the question.
If there is no more question, I suggest we can thank Sebastian and all the afternoon speaker again. Thank you.
Thank you so much for organizing this.
And thank you for the art picture. It was lovely.
Thanks.
Bye.
Bye, everyone.